Welcome back. In today's lecture, I'll be giving an introduction of imaging modes in ultrasound. We already know that in ultrasound imaging, we visualize the internal body structures, and we use this by different imaging modes. There are several imaging modes that can be done with ultrasound. For instance, A mode, which is amplitude mode, B mode stands for brightness mode, M mode, which is motion mode, and Doppler mode. And there are several different types of Doppler modes that we will discuss today: continuous wave, pulse wave, as well as color and power Doppler. First, we'll discuss A mode, which is amplitude mode. A mode is based on the pulse echo ultrasound technique, and what it does, it shows the instantaneous echo signal, amplitude versus time after transmission of the ultrasound pulse. In a previous lecture, I had shown a schematic of a transducer here, imaging a tissue that's consistent of a fat layer, a muscle, and air. We also talked about the differences in the acoustic impedance between various interfaces of the two types of tissues, and we know that there is an acoustic impedance mismatch between the fat and muscle, as well as an impedance mismatch between muscle and air. And because of this acoustic impedance mismatch, there will be an echo coming back to the transducer. And we want to quantify at what time of that echo will come back. So we introduce the range equation, which is as follows here. We have t, which is the arrival time, equals 2 times d, which is the distance from the transducer to the interface. All of that divided by c, which is our longitudinal speed of sound. Once the echo is being collected to the transducer, when we plot the echo, it will look something like this, where we have the echo amplitude as a function of time. And we see two noticeable echoes coming from the fat muscle layer interface as well as the muscle air interface here. The A mode only displays the echo data from a single beam line, which is a limitation of the A mode technique. In a previous lecture, I also gave a question of at what time will each of the echoes arrive to the transducer. So we were given that the distance of the transducer to the fat muscle interface as 5 millimeters. We also were given that the distance from the transducer to the muscle air interface is 15 millimeters. And we assume with the ultrasound system that the speed of sound is 1540 meters per second. We asked the question, when will a 2 microsecond ultrasound echo arrive at the transducer from the first fat muscle interface and the second muscle air interface? So we use our time of flight equation here, our range equation, and we plug in the values for the distance from the transducer to the fat muscle interface here. We try to make sure that the units are similar. So 5 millimeters will turn into 0.005 meters. So it's important to pay attention to your units. And we also plug in the value for the speed of sound, which is 1540 meters per second here. When we calculate, we would get this kind of value, and we convert it to microseconds, which is typically the time duration of ultrasound pulses, and we get 6.5 microseconds here. So our signal that is coming from the fat muscle interface will arrive at 6.5 microseconds. Similarly, we apply the same range equation here, plug in the values for the distance from the transducer to muscle air interface, and we get 19.5 microseconds here. So our echo from the muscle air interface, since the sound will be traveling at longer distances, deeper into the tissue, the echo will appear at a much later instance of time, in this case 19.5 microseconds. So hope you got this answer from the previous lecture. Now, A-mode ultrasound is not that very common in a medical ultrasound diagnosis, but it's widely used in ophthalmic ultrasound or eye ultrasound. And this is used to get different dimensions of the eye, especially in an application called lens placement in cataract operations. Although it's not that used in modern ultrasound diagnosis, is heavily used in non-destructive testing of different structures, such as in non-destructive testing of railway tracks to look for cracks, or aircraft wings, as well as steel structures. So this is beyond the scope of the class, but it's widely used for non-destructive testing applications. The next mode that we will discuss is called B mode, or brightness mode ultrasound. So what we have here on the left is a schematic of our transducer. It can either be a single element transducer or an array of multiple elements here. So if you have a single element transducer, that transducer would move in this horizontal or lateral direction to be able to look at the entire imaging field of view. If you have an array of elements, those multiple elements would already cover a wide range of view. So what we have here is our transducer. It will send the ultrasound signal towards a tissue of interest, and then what we would get is the tissue echo right here. When we collect that echo and post-process it to get the B mode image, one needs to look at the brightness of the echoes. And the way we do that is looking at the amplitude of the envelope. And the envelope is being detected from the A mode signal via a process called the Hilbert transform. So once you get the envelope, if you look at the signal here, now this image here is now as a function of depth in the vertical direction. So from your raw RF data or your A mode signal, you get the signal envelope here. And this signal envelope trace is based off of one location of this B mode image, right here, one line. And so what we do to get this B mode ultrasound image is that we scan at one location after another, line by line. We would move the transducer, or for an array, we would move the area at which the ultrasound beam will assess. So in this case, we're moving from left to right here. And as we go on along, we had multiple A lines that are stacked together side by side, right here, until it forms an entire ultrasound B mode image right here. So again, a B mode image is just a vertical stack of A lines, right? And the nice thing about a B mode image is that it can give a two-dimensional information about a tissue cross-section. And what you would get in terms of the display, the grayscale image, is that the grayscale level will depend on the brightness of that echo, so the echo amplitude. The higher the echo amplitude from that structure means that in the B mode image, it will appear more white or brighter. Here are some examples of B mode ultrasound. Here, a common application where B mode ultrasound is used is in fetal ultrasound to image a baby. So what is typically done is an ultrasound transducer is placed on the belly of the mother, and you can get a B mode image such that like this. So you can see that because of the different structures of the baby, you can quite outline the baby really well right here. Another common example of B mode ultrasound is in echocardiography, or ultrasound of the heart. And you can see here, this is what an ultrasound image of a heart looks like. And since B mode has high frame rates or high pulse repetition frequencies, you can actually image a moving object in real time. So what you're seeing here of the heart is you're seeing the chambers of the heart. And in the chambers of the heart, you have blood. Blood is less scattering than the other tissues of the walls of the heart. Therefore, blood is not so bright compared to the tissue that are in the heart here. So you can see the chambers that are darker and then the walls of the heart that are lighter. And there's also some valves in the heart that is also more dense than the blood. And you can see them moving right here as the heart is beating. When we talk about looking at the different amplitudes in a B mode image, right, we talk about in terms of echogenicity. So is a structure more bright than another structure in that image? So there are several terms that you will hear when we talk about the echogenicity of a B mode image. For instance, if you have structures that appear darker than other structures around them, then they are considered hypoechoic. Okay, hypoechoic structures. And there are some structures, isoechoic structures, that have the same brightness or echogenicity as the other tissues surrounding them. And if there are structures that are more echogenic or brighter than the surrounding tissues, these are called hyperechoic structures. So if you look at this image of an ultrasound phantom here, now an ultrasound phantom is a tissue mimicking material that mimics the echogenicity of different structures of the body. So in this ultrasound phantom, there are wire targets, point wire targets that appear like point-like spots here in this image. So these wire targets are typically echogenic, more echogenic than the surrounding tissues or the surrounding parts of the phantom. Therefore, they're considered hyperechoic structures. There are also structures in this phantom that are less echogenic. So these are more of less or hypoechoic structures. And some more clinical examples of B-mode ultrasound here. For instance, we have this B-mode ultrasound of a gallbladder, and a gallbladder typically filled with fluid right here. But when there is a stone or sediments in the gallbladder, we know that stone typically has a higher acoustic impedance mismatch with surrounding tissue. Therefore, the stone will be more reflective. So you can see here nice B-mode image of a stone in a gallbladder right here. Another application is if you want to look at cysts in the tissue. For instance, in this case, prostate, this is an image, a B-mode image of a prostate with a cyst right here. Cysts are typically filled with fluid and therefore they're less echogenic compared to the surrounding tissue. So these are just some examples of what B-mode ultrasound images look like in the clinic, and these images can be used for various clinical diagnoses. Now we've talked about A mode. A mode typically gives a one-dimensional signal. And we talked about B mode, how B mode is a stack of A mode lines together to stitch into one 2D image. Now we can also, if we use a matrix array transducer, or if we use a linear or a phased array transducer and we mechanically scan that across a 3D volume of interest, then we get what's called 3D ultrasound. And if we collect a 3D ultrasound image over time and we process it, and that has capability for live imaging, as in 4D ultrasound. So on the bottom image here, I show a nice 3D ultrasound image of a baby. Now this kind of procedure is typically used nowadays because the parents would always want to see what their baby's face would look like. But we'll talk about later some safety consideration of this type of imaging technique. Also here on the right, I show some B-mode ultrasound images of different cross-sections of the heart. Nice thing, you can also look at the 4D ultrasound image of the heart valves here. So what is moving actually in this structure are these heart valves that are opening and closing every time the heart is beating. So this type of image is nice because if there are anything wrong with the heart valves, then the sonographer will be able to see and diagnose that type of valve disease. Now let's talk about M mode. So M mode stands for motion mode ultrasound. And what this is, it helps represent motion of tissue structures over time using B mode images. And what you can see here, so this is a B mode image of a heart, for example. And in M mode ultrasound, you take one lateral location, so one M mode line, and you look at that location, the echoes of that location as a function of time. So this bottom ultrasound image here is actually one M mode line imaged as a function of time. And not to be confused with the arrival time of ultrasound pulses to the transducer. What this is actually showing is the time in terms of on the order of seconds. And this depends on the frame rate or the pulse repetition frequency of your ultrasound system. We also are going to talk about Doppler ultrasound. And what is the basis for Doppler ultrasound is this Doppler effect. So you might have heard of this in your physics class. This effect was first defined by Christian Andreas Doppler in the 1800s. And what the Doppler effect is that whenever you have a source of a signal, a source of a wave here, and that wave is also moving, then depending on the location of the receiver. So for instance, here we have a listener. You have a car moving from left to right, and you have a listener that is facing on the direction of the car. So that listener will hear a sound that is of higher frequency. If you have a listener in the back of the car as it is moving further away, then you will hear a more lower frequency sound. So you must have experienced this when you're standing on the streets of the city, right? A ambulance passes by. As the ambulance moves towards you, you hear a high frequency sound, but as it moves away from you, then the sound becomes lower in frequency. So this is the Doppler effect. And what it is used in ultrasound is that it also images any moving tissues, such as it can measure the velocities of blood flow. And blood is what's moving in your blood vessels. And the way it measures the Doppler effect is that we look into the Doppler shifts. Okay? So here is the equation of the Doppler frequency shift, which is denoted by F and D. Okay, so what we're doing is here is our transducer and here is a blood vessel. Now the transducer is sending a signal with a frequency of Fi. So this is your incident ultrasound wave, and that is at some angle theta, some angle relative to the flow of the blood, which is represented by this V vector right here. And then here in your blood vessels, you have multiple blood cells that the ultrasound will be tracking. So when the incident wave goes through, interacts with one of these blood cells, a reflected signal is being received of a frequency Fr. Since the red blood cells are moving sort of away from the transducer, then the sound that is being received will be in a lower frequency compared to the frequency that is being transmitted. So what one can do is can plug in some values for calculating the Doppler frequency shift here. We have our V parameter here, which is the blood flow velocity. So the velocity at which the red blood cells are moving in the vessel. We have theta here, which is the angle between the direction of the blood flow here and the ultrasound incident beam. That is also called the Doppler angle. We also have the speed of sound here, in this case, the longitudinal speed of sound. And all of this multiplied by the frequency of the incident wave here. So to compute what the blood velocity would be, you can rearrange this equation and get one of this form, which is the blood velocity equals the Doppler shift times the speed of sound. All of that divided by twice that of the frequency of the incident wave, cosine of the Doppler angle right here. So this is what the Doppler mode ultrasound calculates. And here's one example of a Doppler ultrasound here, where now we are imaging of the inferior vena cava. So the inferior vena cava is one of the large blood vessels or one of the large veins that send blood back to your heart. It's a fairly large vessel here. And what this examination is doing is that it's looking at the blood flow of that inferior vena cava. So here we trace out a location at which Doppler ultrasound will be assessed, and here is where the blood flow. This line is actually what is orienting the angle, the Doppler angle here. And at the bottom, you can see this is actually the spectrogram of the blood velocities that's being calculated as a function of time right here. So what this is showing you is that the blood flow velocity is somewhere between, minus 0.57 a certain distance per second to positive 0.57 here. Other Doppler modes include continuous wave Doppler. And what this involves is there are two crystals, and typically one is in continuous transmission mode. And here's an example of the transmitted signal here from one crystal, and that interacts with a portion of the tissue, and a signal being received back that is shifted in its frequency here. Typically, although there are two crystals, it can also be mounted into one transducer case. The advantage is that it has accurate display of flow without aliasing. In another lecture, we'll talk more deeply into what aliasing means in terms of Doppler ultrasound. A disadvantage of this, since it uses a really long duration continuous mode signals, is that there is no time delay information of the structures that you're imaging. So there's what's called range ambiguity. On the other hand, if you have pulse-wave Doppler, that type of disadvantages is covered. So what pulse-wave Doppler does, is that it has one element that sends a short ultrasound pulse and also receives that same that echo from that object. So the advantage is, since it's using short ultrasound pulses, there's good range resolution. A disadvantage is that it's unable to measure high velocities, and again, aliasing is a problem, which we'll discuss more in a subsequent lecture. Another Doppler mode is called color Doppler. And what this is it gives a 2D Doppler image of blood flow. In this case, a color Doppler image consists of a red and blue color map, wherein red is typically denoted as when the blood flow is moving towards the transducer, and blue is denoted as when the blood flow is moving away from the transducer. So this red and blue image display is quite nice because it gives the directionality and the velocity of the blood flow depending on the intensity of the blue and the red. So what we show here are the femoral and the deep femoral vein, which are the blood vessels that supply blood to the legs. And this is a nice color Doppler image of a femoral artery, which the blood flow is moving towards the transducer in red, and of the deep femoral vein, which the blood flow is moving away from the transducer. So you see that femoral artery brings blood towards the legs, and the femoral vein brings blood away from the legs. So they are moving into opposite directions. So you can see that nicely, how the blood flow is in opposite directions in a color Doppler. Another application for this is when you're imaging the flow of the carotid artery. Now, what is the carotid artery? It's actually important blood vessels that supply oxygenated blood to the brain. And if there are any narrowing in the carotid artery, then that will prevent oxygenated blood from going to the brain, which can cause some damaging effects. So it's a common procedure to look at the carotid artery using color Doppler. And what you would see here is a nice red profile of the blood flow of the carotid artery, as well as its velocity spectrum here. The next ultrasound Doppler mode is the power Doppler. Now, this is a more sensitive mode compared to color Doppler, and the reason being is that it focuses more on the intensity, so it doesn't look into the direction further. So all the image processing are only focused on the intensity of the ultrasound, and that improves the sensitivity to the amount of blood flow. So it's useful also for examining very low velocity blood flow. For instance, in this case down here, it's an ultrasound power Doppler image of an abnormal tendon with some small blood vessels or neurovasculature. So typically in a color Doppler image, this might not be seen. But for power Doppler, because it's more sensitive, then you can see the really small blood vessels quite well. Now, in summary, I've given you an overview of the different modes of ultrasound. We talked about A mode ultrasound, which is a one-dimensional signal of the ultrasound echo coming from a tissue. We talked about B mode ultrasound and how that is a stack of A mode ultrasound signals to create a two-dimensional image of the structure of interest. We also talked about M-mode ultrasound. And M-mode ultrasound is widely used to look at motion of the tissue, especially in echocardiography applications. And we also talked about Doppler. Doppler mode imaging is used for mapping the blood flow in tissues. We also talked about how ultrasound can be used also for 3D as well as 4D ultrasound, looking into changes in the tissue motion as a function of time. We talked about echogenicity, how to characterize the images as having structures that are more hyperechoic, hypoechoic, and isoechoic. And finally, we had an overview of the Doppler effect as well as the different Doppler modes that are used in ultrasound. And in subsequent lecture, we will talk about Doppler ultrasound in more detail. So that's it for today's lecture. Looking forward to seeing you in the next lecture.